Hello, everyone. This is Qiang from the Hong Kong Polytechnic University. I'm very glad to present our paper, Model-Based Head Orientation Estimation for Smart Devices. This is a joint work with my supervisor, Professor Yuanqing Zheng. We know that the voice command has become the main user interface to smart devices. Nowadays, a family typically has many smart devices, such as smart speakers and smart home appliances. However, in real life, a voice command may wake up multiple devices at the same time. For example, imagine that there are many smart lights in your home. When you say, turn on the lights, all of them get a command and turn on. Otherwise, you must say, turn on the left lights or turn on the right lights. But if the smart lights can infer your head orientation, you can just say, turn on towards the intended lights, then it will vibrate. So the head orientation can provide a contextual clue of the voice command for smart devices. Then we may ask a question, how to estimate the user's head orientation? We summarize the related works in coordinates with 2 dimensions, number of microphone rays and training intensity. We can see that the existing model-based approaches basically require many microphone rays, and the existing machine learning-based approaches need too much training overhead. Both kind of the existing solutions are not friendly to users. So in this work, we propose the Hui at the left bottom corner. Hui is a model-based solution, so the training overhead is very low. Also, it works with only 2 arrays, which is more practical to users. The principle behind Hui is the voice radiation pattern. Human voice is not radiated uniformly to all directions, blocked by the mouth and head. More energy is radiated in the human's forward direction. We can formulate this pattern as a mathematical function with a different direction. In this way, suppose there are 2 arrays at the different directions. We can have a theoretical energy ratio from our theoretical formula and a real energy ratio from our measurements. Thus, we can minimize this loss between the theoretical and the real energy ratio to find the orientation. Here, you may have a question. The distance difference also leads to the energy attenuation. How to deal with this distance energy loss? Well, we could perform a one-time measurements with different distance in a room to measure these attenuation parameters and compensate the energy loss before performing a head orientation estimation. Okay, so far, we still have a problem. The estimation results is not unique, but always ambiguous, since the voice radiation pattern is symmetric. Thus, we can't obtain the unique results with only 2 arrays. For example, when 2 arrays measure the same energy levels, we cannot say the user is speaking to 19 degrees or 270 degrees. But a key observation here is that these 2 degrees are symmetric about the x-axis. So here the disambiguation problem tends to be detecting if the user is facing arrays or back to arrays. So next step, how to remove the ambiguity with this observation? Well, we can utilize the voice frequency radiation pattern. As shown in the left figure, the high frequency part of the voice has a small wavelength. So it also has a weak diffraction effect through a small mouth. Thus, this signal has a high frequency band is more directive than the low frequency band. When users speak towards the arrays, the array will hear more high frequency signal. Therefore, you can use the high-low band energy ratio to detect if the user is speaking to arrays or backing to arrays, and then remove the ambiguity. We implement Hui on 2 microphone arrays with a laptop. 10 volunteers joined these experiments in 2 rooms. In each room, we mark the locations and orientations in advance at the ground truth. Users are asked to speak voice commands at these locations to each orientation. The left figure shows the CDF of estimation error. Overall, the median estimation error is 23 degrees. The red figure shows the different users have quite similar performance. We also evaluated Huawei in various experiment settings. Please refer to our paper for more technical details and the evaluation results. To conclude, we propose the Huawei, the first model-based work on head orientation estimation with only 2 micron rays. Huawei first leverage voice energy pattern to estimate the head orientation candidates, and then employs the voice frequency pattern to remove ambiguity and obtain the final estimation results. Huawei can achieve a median error of 23 degrees, which is very promising to provide the new context information for the voice commands. Okay, that's all. Thanks for your listening and welcome all questions.